Okay, this is a fairly long problem, so you're probably going to want to pause the video and take notes where appropriate. Over here we have kind of a picture of the right circular cylindrical can. We got a blue top. You can't quite see the blue bottom down here, but you got a top and a bottom. And you're told that the can must hold 11 fluid ounces, and 1 fluid ounce is approximately that many cubic inches. So if the fluid ounces, if this is the number of cubic inches in 1 fluid ounce, if we multiply that number by 11, we'll have the volume of the can in inches cubed. And the volume of a right circular cylinder is pi times the radius squared times the height. So if we put this 19.85 in here for the volume and then divide by pi r squared, we'll have h in terms of r. That's a constraint. And we're going to set up a cost function, which is going to be our objective function, the one that we're going to try to minimize. We're going to minimize the cost. Okay, so the area of the top plus the bottom, it's a circle. So the area of the top is pi r squared. So is the area of the bottom. So there's 2 of those. The lateral surface area, you have to picture, if you want to, cutting down the edge with a pair of scissors and laying open the can. And this is the lateral surface area right here, where h is still the height, but this distance right here is actually the circumference of the circle, which is 2 pi r. So the area of the lateral surface is 2 pi rh. So to get the total surface area, we're going to add those 2 together. So here's the lateral surface area. We're going to replace h with what we found over here. And the pi r's cancel out, just leaving us 1 factor of r in the denominator. So here's the cost function depending on r. The cost depending on the radius is 2. Where'd this 2 come from? Well, that's because the cost of the top and the bottom per square inch is twice that of the lateral surface area. So this 2 is because of twice the cost. And this term, this 2, is just from the formula for lateral surface area. Okay, so there's your cost function. To find out the value of r that minimizes that, we're going to use some calculus. So we'll go to board 2. Here's our cost function. I could have written this as 4 pi r squared. And we're going to take the derivative of this function, c with respect to r. We get 8 pi r, reducing this exponent by 1. Negative 1 times the positive 2 in front is negative 2, r to the minus 2. While we're at it, we'll take the second derivative. We'll apply the second derivative test later. And now we're going to set this first derivative equal to 0 to find the critical numbers. Of course, r has to be greater than 0. Otherwise, we don't have a can. So the derivative here's the first derivative set equal to 0. And then we're going to solve for r. Well, I'd multiply every term by r squared, get our 8 pi r cubed. This cancels out. Take this 2 times 19 to the other side. And so r cubed equals, well, if I put 8 pi under here, dividing by the coefficient of r cubed, this 2 cancels into the 8. So there's r cubed. So r is the cube root of that. And there it is right there. To 2 decimal places, that's about 1.16 inches, because we're a linear measurement. And we had a formula for h in terms of r. So we just put this value of r into there, and there's the height of the can. Okay. And to show that this generates a minimum, we could put 1.16 1/6 into the second derivative to find out if we get a positive or a negative. Well, I don't care what number you put in here for r. This is like over r cubed. 8 pi is a positive number. R cubed is a positive number. It's positive, which means the curve is concave upward everywhere. So this value of r, which has a horizontal tangent line there, creates a minimum surface area. Okay, there you go. Hope that helped. If you have any questions, post a comment.